Okay, the topic is slope fields, and what this is, sometimes we're incapable of finding solutions to differential equations. We just can't solve them, or they're really difficult to solve. But we still want to have an idea what the family of curves that form a solution looks like. And so we can use this graphical tool called a slope field to figure out what the solutions look like, and then we could maybe pick an interesting trajectory from that and we can still use that as a model, right? So how do we do this? Well, if we wanted to, for example, draw a slope field to represent this differential equation, dy dx equals y, all we would do is we'd come down to, we'd take an xy plane, and I've just set this up where I've just put a point at all the we're not going to do all these. I mean, that's like, I don't know, 121 spots that we'd have to fill in little lines. We're not going to do all those, but we could. We're going to come down to an xy plane, and we're going to make little tiny short line segments that represent the slopes of the tangent lines at each of these values of x and y, right? Really what we're doing is we're starting with a differential equation of the form, just an ordinary differential equation. So it's of the form dy dx is some function of x and y, right? We're going to be inputting values of x and or y to calculate the slope of the function at those coordinates, right? Okay. So then we'd come down and we'd make a little table. This is the way I like to do this. Just make a table that's got 3 columns, and we're just going to choose some values. Like arbitrarily, if we started, for example, at something like, how about -5, -5? Well, first of all, the derivative only depends on y, doesn't it? Right? So the value of x is independent. But if I were to pick this value, -y, what's the value? -5, -5. What did they say?
Some of them on assessment.
Oh, yeah, you guys aren't dealing with that. So, yeah. So x is -5, y is -5. What's the value of the derivative then? dy dx equals y, so what's -5, right? I'm just going to plug, the dy dx is given by y, and if y is equal to -5, then dy dx is equal to -5. So I would go to the point with coordinates -5, -5, which is right there, I guess, right? And I'm going to make a line, just a little line segment that has a slope of, well, I'll just write it. Dang it. Something like that, right? I just make a little line segment. Now I know that I could be smart about this, though, because the derivative only depends on y. So really, I didn't need to make this, I didn't even need to write that as -5. I could just call that something like x. It doesn't matter what the x values are, does it? So if, regardless of x value, at y equals -5, the slope is -5, how could I propagate that little mark and make a whole bunch of them at the same time? Like what other little tangent lines could I draw? In what pattern? You see what I'm getting at here? The derivative is independent of x. So I could let x be any value. Let me write it this way. I could let x be any value like, I could let it be any value from, let's say, -10 up to 10. Doesn't matter. If y is -5, the slope is -5. You guys get that I could just, like in a horizontal line here, there, every place where y is -5, regardless of the value of x, I'm just going to draw lines with a slope of -5, right? And I could do the same thing like if I went up to 0. If y is 0, well then my slope is 0. Regardless of the value of x, right? So when y is 0, I'm just going to get a bunch of horizontal tangent lines all the way across. You get the idea? Okay. Well, we don't need to go through this whole process. I got a cool little, I'm pretty proud of this one. This is my, look at this Desmos document here. This is pretty good stuff. So I tell you what, I'm going to put all these Desmos documents in a file, and you guys can have, I'll share them with you. So you can make a Desmos account, and definitely you want to grab these things and just have them, because these are, I got some pretty good ones that you'll use in college if you're going to take some math classes. At the risk of sounding immodest, these are pretty sweet. So you can choose here the number of, like the boundary, where do you want to draw your little tangent lines? Where do you want to create your slope field? So we're going to go from -10 to 10 on x, -10 to 10 on y. You can choose the number of slope fields you want. Okay, like if we wanted to do 20 of them. There it is, right? And then you can even choose the length of the, now I modified one that was already on there, but this is a little cooler. So you can look at the little, decide how long you want the tangents to be. And then look what this is doing. It's creating, if you look at the patterns of all these little tangents at each of the points, it's giving you an idea what that family of curves must look like, right? You guys see that? Like if I were going to start with a point, you can kind of see I can trace a trajectory here. Let me take a picture of this. There we go. So if I wanted to create a trajectory here, I could just, like pick a value. It looks like it's doing something like that, right? With these. Can you see that that's what, and then down here it looks like it's doing something like that, right? Everybody get that? You're just following, I didn't do that very well, but you get the idea that you're just following the little tangent lines, and it's telling you that it's like a road map telling you what's the slope of the curve going to be in this region. And because these are all aligned horizontally, we know that when we pass through a certain x value, it's got a certain slope here, right? I've got this built so it'll actually, if I come, I can turn on. I just solve the differential equation, and then you can plug in the. Oops, that's not the one I want. There it is, right? So you can see some trajectories through that family there, and it's just you can see how those align with the directions of the slope fields. Okay, do you get the idea how that works? How that can be useful? It's super easy concept. It's almost not even calculus. You're not really solving any differential equations. You're just representing the information in the differential equation graphically is all. Okay, give me 1 to 5 on that. Is that making sense, what we're doing here? Okay, let's look at another one. Okay, so we did that. We drew a slope field, and you see how I could have used that table and just made a whole ton of these things. I'll tell you, here's something else that's kind of you could do on Desmos. While we're at it, let me show you something else we could do. How you could use the, oh man. I could make a table out of this too. I could do, let's see if I can do this. If I do like f of x, y equals y. Oh, how come it won't let me do a table there? I don't want to waste too much time on this, but let me see if I can just do a table here real quick. So if I do a table where I've got, yeah, there we go, x1, y1, and then I could do there you go. Okay, so that works. You can make a table out of this then. Like I could generate what the function is down here. That's the derivative function, and then I can just pick values. I could just randomly pick values then, and look what it's going to do. It's just going to. I can make a table out of this, right? In other words, where it'll build a table quickly for me, right? You get the idea. Oops, how come it's not doing that? Oh, it's because I had to do that. I don't know why. Hey, I don't want to mess around with it. You get the idea. Okay. Or you could do that on a like sheet, Google Sheets, or on Excel or something too. Okay, let's try another one. Draw a slope field that represents solutions of this function. Okay. Well, now I'm going to do the same thing. I'm going to create a table. I've got this quadratic function in x. Now let's talk about this one a little bit. Notice that the derivative is independent of y this time. Can you tell me what that implies? When I'm drawing my slope field, if the derivative function, so the slopes of the curves, right? The slopes of the little tangents I'm going to draw are independent of y. What's that tell me? What's the pattern going to be? It's going to be based on x, isn't it? So if I pick a value of x, if it's independent of y, the slopes that align at all the points, the slopes for the points that align vertically are all going to be the same, right? Because there's no y that shows up in my derivative function. You get what I'm saying? So it doesn't matter what y is. It's not going to change the value of the slope, right? So all we'd have to do then is just pick some values of x, and that's sufficient. Like if I pick x equals -2, what am I going to get here? 4 plus 4 is 8, minus 3 is 5. Did I do that right? I think so. Right? And so at x equals -2, I've got these kind of steep slopes. If I pick 0, I'm getting -3. So at 0, I've got stuff that's, kind of like not quite as steep, but negative. Right? What about at -1? -1, I'm getting 0. Everybody see that? 1 plus 2 minus 3. So at 1 I'm getting, is that right? Yeah. Right? At 1 I'm getting 1 minus 2 is, so negative 4. A little bit steeper. Let's just do one more. And then at 2, what am I getting at 2? 4 minus 4, so minus 3. So it looks like it's getting a little bit more gentle again. And I could do that everywhere and create a slope field, right? Again, I got this pre-built, so let's just look at an example of what this one looks like, and there it is. So there's that slope field, right? Let me. I must have made a mistake there. Did I put a different? Is that the wrong equation? Well, maybe not. Oh, there we go. Okay, so that works. Yeah, there. Now that matches up with ours. Look, we get at -1, we get our 0. It looks like it's really steep over here. It rounds off to 0. I mean, you can get a pretty good idea what this thing's going to look like, right? They wanted us to chart, to plot a trajectory through the point 0, 2, right? We've got all this family of all these curves that match this slope field. They want us to do two things. They want us to draw the family of curves, sketch the family of curves. Okay, well, what are those going to look like? Just kind of like that, right? Does that make sense? Steep, increasing over here, getting less steep, horizontal tangents at -1, getting steep in a negative direction, less steep. If we kept going on our table, we would have found that we had a 0 at 3 for our derivative, and then they ramp back up. Okay, that makes sense, doesn't it? Because if the function is quadratic, what's the derivative gonna, or the antiderivative gonna be when we integrate? Like if I were to take an integral of this function, x squared minus 2x minus 3, what am I going to get from my integral? It's going to be cubic, isn't it, right? Well, looks like a family of cubic functions, right? We just want to find the one now that goes through the point at, what was it again, 0, 2, I think. So right there. If I want to pick the one that goes through 0, 2, I could solve for C, right? I actually solved the differential equation down here. So if we plug in 0 for x and 2 for y, what do we get? 2. So I could plot the function. I mean, there's no, like you wouldn't be doing this part because this entails, the whole point of the slope fields, you don't have to solve the differential equation. But we could have just drawn this without solving it. I just want to draw the trajectory so we can see what it looks like. What color do you want? How about green? And there it is. Everybody see that? Make that a little thicker. Okay, there's the trajectory through the point 0, 2. Right? Everybody get that? I'm just tracing the one. I'm starting at 0, 2, and I can see what the slope fields look like, and then I'm just going to follow that around. It's going to round off, and then it's going to get, it's going to get steep over here. It's going to get hit a 0 there, and then get steep again. Is it perfect? No, it's not perfect. I mean, our hand drawing that from a slope field isn't going to give us an exact trajectory, but a pretty good idea what's going on. At least it does tell us some interesting things. It tells us, like, what's the kind of stuff we looked for before. A lot of times we'd look for places where we had peaks and valleys, right? Relative extreme, but we get those, right? We can find where those occur, okay? Give me thumbs. Is this making sense? Okay. Maybe just look at one more. Okay, so what about one like this? This is, I want to look at this guy. So we get derivative equals y minus x. Now, this is a tougher one. This is not an ordinary separable differential equation. There's no way for us to separate the x's and y's, and so this is one you wouldn't learn how to solve until later on, until you started taking an ordinary differential equations class after you get done with your calculus series. So it would be off the table for you to solve right now, but we could still pretty easily draw a slope field to represent it. So how could we do that? We can make a table where we just plug in values of x and y, but we could look at this a slightly different way. What if we were to pick values of the derivative here? Like if I were going to pick, I want to find the places where the derivative is equal to 0, okay? Well, if I pick the values where the derivative is equal to 0, I just get the equation 0 equals y minus x. If I solve that for y, I just get y equals x, right? Well, then doesn't that mean that every place along the line y equals x, all the points that fall on that line are going to be places where the derivative is equal to 0. Oh, thank you. Where the derivative is equal to 0, right? Everybody get that? Andrew, you got mail, buddy. Right, so we could go in on our slope field then. And another, like maybe an easier way to represent that would be to say, if I'm just going to let the value of the derivative equal k, I'm starting off with y equals x. If I solve for y, I just get y equals x plus k. Well, here remember we're representing dy dx as k. Choose the value of the parameter k, which represents the slope. It just looks like a constant then, right? It's 0. If k is 0, we get the line y equals x. And so every place along the line y equals x, those are all the places where we're going to get right? Those are the places where we're going to get horizontal tangents. And look at the distribution. Those are just the points that lie along the pattern y equals x. If I let k equal 1 or the slope equal 1, now those are going to lie along the line y equals x plus 1. Well, that's just, what are we doing here? The slopes are 1 and we're just moving up by 1. So then these slopes are going to be 1, right? So every place along this line we're getting slopes of 1, right? If I go up here to 2, that's along the line y equals x plus 2, so these are going to be a little steeper. So that's what we get, right? So we could fill this thing out pretty quickly if we use strategies like that. Okay, and then what's this look like if we see the whole slope field? Just looks like this. Okay? Make sense? So it looks like there's some kind of like a slant asymptote here maybe, right, that these things are sticking on, and then they're going to peel off and get steeper upward and peel off and get steeper slope downward below. So trajectories look like look like that. Does that make sense? Okay, that's pretty cool. Don't you think that's a pretty cool way to approach it? Very clever. All right, so another kind of question that you're going to see is stuff like that. Like on the AP test, this is the kind of stuff, I remember, you see a lot of these. Which of the following differential equations could have the slope field shown in figure 7? How would you check that? Yeah, you just try some values and check it out, right? So like if we pick, well, for one thing, look what happens right here. When x is 0, you get horizontal tangents everywhere. When x is -1, what's one thing you notice? There's a vertical matching of all the slopes, right? It looks like it's independent of y, doesn't it? The slope only depends on x. So what's that mean right away? Which ones could we cancel out for sure? B and D, yeah, exactly. Right, those we can cross right out because look, the slopes depend on y's, and clearly that's not the case. It only depends on x. So then we just have to match, see which one fits, A or C. Well, it looks to me, well, you guys tell me, what's this mean? The slopes, if I pick a negative value of x, are the slopes negative or positive? They're negative. If I pick a positive value of x, they're positive. So what's the answer? It's got to be C, right? It's got to be C. Good? Make sense? Okay. There's that stuff. And then I wanted to look at one more of the growth and decay ones. We didn't do the last example from last time, right? This is the stuff where we were looking at, I think we ended up with radioactive decay, right? We're just solving, that's an uninhibited growth model where we're starting with a differential equation where the rate of change, and the only thing that for growth and decay, uninhibited growth and decay problems, the differential equation is very simple. The rate of change of a quantity is proportional to the amount of the quantity, right? So for population growth, K would be a positive constant. For radioactive decay, K would be a negative constant. But we're just going to solve that differential equation. We always end up with the same result. We just end up with y equals y naught times e to the kt, right? Okay, so what about inhibited growth and decay? What if you're going to grow exponentially initially, but you're inhibited, there's some maximum value that you're going to get to, or you're going to decay and there's some minimum value you're going to get to? That would be stuff that looks more like this. Are you going to grow towards an asymptote? You're going to decay towards an asymptote. Okay, here's the model we set up for inhibited decay. We're going to say that the rate of change of the quantity is proportional to the difference between the value of the quantity and some fixed value, right? So in this case, dy dt equals k times the quantity m minus y, where y is less than m, right? So y is going to increase, but it's always going to be less than m. That's the growth model. The decay model, now y is greater than m, k is going to be a negative constant, and y is going to shrink towards a minimum value of m. Okay? A classic example of this is Newton's law of cooling, which you can flip around, and it works the same for warming, actually. Suppose an object is heated, it's heated up to an initial temperature of U naught. Okay, that's its starting value. Then at time t equals 0, the object is put into a medium with a constant lower temperature, causing the object to cool. Okay, what's going to happen? Well, the object is initially going to cool pretty quickly when it's hot and the environment is cool, but as it cools and its value approaches the ambient temperature of the environment, it's going to cool more and more slowly, right? And so here's the differential equation that matches that. The rate of change of the temperature is proportional to the difference between the object's temperature and the environmental temperature. The bigger the difference, the faster it changes. The smaller the difference, the slower the temperature changes. So we can solve this pretty easily. Let's just do this as a quick reminder of how we solve these things. How would I solve that differential equation? Use my variable. Everything else is constant, including T, right? We're saying the environment is big enough that the little bit of temperature, of heat that's added or subtracted by the object we're dropping into it is insignificant. Like say we're dropping a hot piece of metal into the ocean or something, right? It's not, the ocean's big enough that little piece of metal is not going to significantly warm the ocean. It's going to stay constant temperature. Okay, so what would I do here to solve this thing? Okay, so I'm going to try to separate the variables, right? I've got this expression, I've got my u's, and there's a factor that involves a u and a constant. And then I've got my t's, and I'll leave the k on that side. No reason to move the k. So I'm going to multiply by dt and divide by the quantity u minus t. And I end up with du over u minus t equals k dt. I can integrate both sides, right? What's the integral of du over u minus t? Right, natural log of u minus t. And u is always greater than t, so that's never negative, so I don't need to have any absolute values around this. I can just make it parentheses. Equals, how about this side? What's the integral of k dt? kt, what do I need? I'm not done. I just did an indefinite integral plus c, right? We good? Okay, I want to solve for u though, so I've got to exponentiate both sides, right? That's going to give me the exponential cancels the log, right? So I'm going to get u minus t equals e to the kt times e to the c, right? So I'm just going to call that c. How about? We'll make that c1. So that's c. Okay, we want to find the value of these constants. Well, one I could choose is when t equals 0. If I let t equal 0, what am I going to get? I get, this is really u of t, right? So I get u naught minus t equals c times e to the 0 is 1. So the value of c is just the initial difference in temperature, right? And we could rewrite this thing as u of t minus t equals c, which is the quantity u naught minus t, the initial temperature difference, times e to the kt, right? If I solve for u, I just get t plus u naught minus t e to the kt. Or I could put the t at the end if I want to. I'm not sure how they did. I'll probably put it at the end. Yeah. Okay? Make sense? Okay? So let's look at one quick example. If an object is heated to 90 degrees and allowed to cool in a room with a constant ambient temperature of 20, if after 10 minutes the temperature of the object is 60 degrees, what will its temperature be after 20 minutes? Okay. So, oops. We already solved the differential equation, so let's just steal that. So what are the values from our problem that we're going to be plugging into our solution? '90s what? Do you not? Okay. What's T? Looks like T's 20. And T, when T, well, we have an ordered pair, don't we? When T equals, I guess we're doing this in minutes, when T equals 10, what's the value of U, the output? 60. Okay, so there's an ordered pair that corresponds to that, right? Because our input is time, output is U, right? It's temperature. Okay, so how are we going to solve this thing? We still have to know, there's one unknown that we haven't solved for yet. Everybody see that? Okay, we need to know what the decay constant is. That's what this initial condition is telling us, right, or boundary condition. So then if we plug all that stuff in, we get 60 equals 90 minus 20. So the change in temperature is 70 times e to the 10. Oops. K plus 20. I just got to solve for K. So if I subtract 20, divide by 70, I'm going to get 4/7 equals e to the 10K. Log both sides. Log 4/7 equals 10K. So K equals log 4/7 divided by 10. Now all I've got to do is plug that back into my differential equation right there. Along with my other constants, and we have our solution. So U of T equals 70. We'll just call that 70 e to the log 4/7 over 10 times T plus 20. If we want, they want us to figure out what the temperature is going to be after 20 minutes. So all we have to do is plug 20 in. U of 20 equals 70. E to the 20 over 10 is 2. So e to the 2 log 4/7 plus 20. Throw it in a calculator and we got it, right? So when you're cooking a turkey on Thanksgiving, you can bust out Newton's law of heating to know when your turkey is going to hit its safe temperature. Just do a couple measurements, get a boundary value with a little experimentation, and you can pretty precisely determine when the turkey is going to be done.